Hi guys, we're looking at 1986 free response question number 1. We have a Atwood's machine with a 4 kilogram, a 2 kilogram, and a 1 kilogram hanging over the edges. First we want to find the acceleration of the 4 kilogram block. Well, while this is a system, I will, instead of just trying to find the acceleration of the 4 kilogram block, I'm going to find the acceleration of the entire system when this is released. So what I'll be doing is drawing a free body diagram for each of these masses, and I'll color code it so that anything that is in the direction that the system moves, I'll do in green, and anything that's against the motion of the system, I will do in red. So for the 4 kilogram object, I have a weight that I'm going to call FG4, and I have a tension in the string pulling against it. I'll call that FT1. If I continue to follow that string along, up over the pulley and down to the 2 kilogram, this same string is pulling with a force of T1, and it's in the direction that the system moves. And then, of course, I have downward the weight of the 2 kilogram. I'll call that FG2. So I'm trying to show with the size of my vectors that the direction of the acceleration is downward for the 4 kilogram and upward for the 2 and the 1 kilogram. So I have the weight winning over here, but on the 2 kilogram I have the tension winning. And then we have also, in addition to the weight of the 2 kilogram, we also have another tension. So let's call that FT2. That is a second string. I don't expect that tension to be the same as the tension in the first string because, again, I need the upward forces to win on the 2 kilogram in order to get an upward acceleration. We can transfer that tension in the lower string as a FT2 on the 1 kilogram, and then I'll draw the weight of the 1 kilogram, and I got to make this really small. So the FG of the 1 kilogram is allowing the 1 kilogram to also accelerate upward. So basically, everything on the left has an upward acceleration, and the 4 kilogram on the right has a downward acceleration. Since they move together with a tight string, they're all going to have the same magnitude of velocity and magnitude of acceleration. So that allows me for part A to just sum the forces on the entire system and set that equal to the mass of the system times the magnitude of the acceleration. So I'll do that by summing all of the forces. So starting with FG4, that's in the direction of motion, minus the tension on the 4 kilogram, we called that T1. Keep following that string back over to the 2 kilogram. You have an FT1 in the direction that the system moves. Then you have a weight of the 2 kilogram against the motion of the system and a tension in the second string. We called that FT2. And then moving down to the 1 kilogram, you have FT2 upward in the direction of the acceleration, and then downward we have the weight of the 1 kilogram FG1. Okay, so that was a lot. We were summing the forces on the entire system, but what we should notice is we have these internal third law pairs that cancel out, right? These two tensions, one red, one green, one red, one green, they're going to cancel out. And what we're really looking at for the system is just that the weight of the 4 kilogram is kind of leading everything, and it's going to have to pull against the weight of the 2 kilogram and the weight of the 1 kilogram in order to accelerate the system. And all of that should equal the mass of the system times acceleration. So if I want the acceleration, I'm going to do FG4 minus FG2 minus FG1 divided by the mass of the entire system. Or for a 4 kilogram object, that's a weight of 40 newtons. A 2 kilogram object is a weight of 20, and a 1 kilogram is a weight of 10 newtons, all divided by the mass of the system. So 4 plus 2 plus 1, or 7 kilogram. So we have a total of 40 minus 20 minus 10 divided by the 7, and I'm coming up with an acceleration of about 1.43 meter per second squared. Okay, so that system approach does make this a little bit simpler than trying to solve a system of equations. But the one thing that it does is it eliminates those tensions. We don't need to worry about them when we sum the forces on the system. But maybe this is a qualifying type thing where the tension would break or the rope would break after a certain tension. So in part B and C, they're asking us to go back in and find the tensions in those strings. So that's what we're going to do next. I'm actually going to start with the tension in the 1 kilogram block. And I'll do that because I like to find the tensions when they're in the positive direction. I certainly could go to the 4 kilogram and solve for T1 that way. But I'm going to go to the 1 kilogram and I'm going to solve for tension 2, which is the upward tension on the 1 kilogram. And the way that I'll do that is I will sum the forces on the 1 kilogram. And that would be equal to Ft2 minus Fg of the 1 kilogram, and that should be equal to the mass of the 1 kilogram times acceleration. Now, the nice thing about having the system acceleration, I know that each of the blocks has the exact same acceleration as well. So if I want to find Ft2, then I would just add Fg1 to the other side. So that's m1a plus, well, weight or m1g. So that will be my 1 kilogram times the acceleration 1.43 plus the mass, again 1 kilogram, times 10. So we have, well, I can do that one in my head. It looks like it's about 11.43 newtons, okay? Now that falls within the range that I would expect because I know that the tension in that string has to be larger than 10 newtons and to allow the 1 kilogram to accelerate upward. So for part C, I have the tension in string 2 is 11.43 newtons. Now that will allow me to find the tension in the upper string, so Ft1, and I'd like to use the 2 kilogram to find that only because Ft1 is in the positive direction for that free body diagram. So I'm just choosing to do that for simplicity. So now I'll go back in and I'll do part B, and I will sum the forces on the 2 kilogram, and that is, we have Ft1 in the upward direction minus the weight of the 2 kilogram minus Ft2, and that should equal the mass of the 2 kilogram times acceleration. And again, I have the acceleration of the system, so I'll apply that acceleration to the 2 kilogram individually. And if I want Ft1, this is why I chose to do the 2 kilogram free body diagram. I just add everything else to the other side, and I don't have a negative in front like I would have if I tried to solve the 4 kilogram. Not a problem, you could do that if you want. But this would be equal to m2a plus the weight of 2 plus tension in string 2. So we have m2 is 2 kilogram times the acceleration of the system, which is 1.43, plus the weight of the 2 kilogram, or 20 newtons, plus the tension in string 2, which we said was 11.43. Now, before I actually put that into a calculator, I just want to get an idea of what the range should be. So in order for the 4 kilogram to drop, I know this tension has to be less than 40 newtons, and I know it also has to be greater than 30 newtons because this tension in string 1 is what's going to bring these 3 kilograms upward. So I'm expecting something between 30 and 40. So let's see what we end up with. If I do mass times acceleration plus 20 plus 11.43, I'm getting a tension in string 1 of 34.29 newtons. So that again falls within the range that I expected. It is large enough to lift the 3 kilogram, but it's also small enough to allow the 4 kilogram to fall. So it was somewhere between 40 and 30 newtons. So part B, we have 34.29 newtons. Okay, so that is it for 1986 for response number 1. Thanks for watching.